Hey there, this is Mehta Kumar, and today I'm here to give a brief description about data encryption. Okay, let's see what's encryption. It is a process of converting the plain data into a encrypted data by means of a key that is unreadable unless the user has it. This ensures that though the data is stolen or accessed by an attacker, he cannot read or understand unless he has a key to decrypt it. Okay, there were actually two types of encryption keys available for data encryption, and there were the symmetric key and the asymmetric key. The symmetric key is also known as the public key, and the symmetric key is even known as the private key. Okay, let's go with the symmetric key. In this method, the sender encrypts the data with one key, sends the data as a ciphertext, and then the receiver uses the key to decrypt the data. Whereas in the asymmetric key, it is quite different. The user uses two types of key for encryption and or decryption. With this method, a public key is freely available for everyone and is used to encrypt the data, and the private key is used by the recipient to decrypt the data. Okay, let's go with the other stuff in it. There were three levels of encryption, namely the storage level encryption, application level encryption, and the database level encryption. Let's go with the storage level encryption. In this level of encryption, the data is stored in the subsystem and thus protects the data at the rest. It is well suited for encrypting files and entire directories in an operating system context. From a database point of view, storage level encryption has the advantage to be transparent, thus avoiding any chances of existing applications. And let's go with the application level encryption. It moves the encryption or decryption process to the application that generates the data. Encryption is thus performed with the application that introduces the data into the system. The data is sent encrypted to be finally decrypted within the application. This approach has the benefit to separate encryption keys from the encrypted data stored in the database, since the keys never have to leave the application aside. Whereas in the database encryption level, this is quite different. Everything happens in the database end. It allows securing the data as it is inserted to or retrieved from the database, so that the encryption strategy can thus be a part of the database design and can be related with data sensitivity or user privileges. Selective encryption is possible and can be done at various granularities, such as the tables, columns, or. Okay, now let's go with the popular encryption standards which are available for the data encryption. These encryption algorithms are very popular and recently and predefined from long years. Okay, let's go with DES, data encryption standard. The algorithm is designed to encipher and decipher blocks of data consisting of 64 bits under the control of 64-bit key. The key itself is 64-bit. A block to be enciphered is subjected to the initial permutation and then to a complex key dependent communication. Finally, to a permutation which is the inverse of the initial permutation. The DES is a product block cipher in which 16 iterations around of substitution and transposition process is cascaded. The block size is 64 bits. The key which controls the transformation also consists of 64 bits. However, only 56 of those can be chosen by the user and are actually the key bits. The remaining 8 are the parity key check bits, hence totally redundant. Whereas in the triple DES, that is, the operation of the DES is being done for 3 times for more security and more encryption. It takes 3 64-bit keys that are overall key length of 192. You can simply type it to the entire 192-bit key rather than entering each of the 3 keys individually. The triple DES then breaks user provided key into three subkeys, padding the keys if necessary so that they are each 64 bits long. The procedure for encryption is actually the same as regular DES, but it is repeated 3 times, hence the name is triple DES. Whereas we go with the TSFS, also known as the transposition, substitution, folding, and shifting encryption algorithm. TSFS algorithm, which is a symmetric key algorithm, its main features include using transposition and substitution cipher techniques that are important in modern symmetric algorithms as they have diffusion and confusion. Moreover, it encrypts only the sensitive data, thus limiting the added time for encryption and decryption operations. This algorithm utilizes 3 keys and expands them into 12 subkeys using the key expansion technique to provide sensitive and effective security for the database. In order to improve the security, this algorithm uses 12 rounds and 2 different keys in each round. However, the TSFS algorithm applies merely to alphanumeric characters. It does not accept special characters or symbols. Coming to the RSA algorithm, this system includes a communication channel coupled with at least one terminal having the encoding device and at least one terminal having the decoding device. A message to be transferred is enciphered to ciphertext at the encoding terminal by encoding the message as a number M, for suppose, in a predetermined set. That number is then raised to a first predetermined power and finally computed. The remainder or the residue C is computed when the exponentiated number is divided by 2 of the product of the 2 prime numbers. In this algorithm, 2 large prime numbers are used for construction, the public key and the private key. It is estimated that the difficulty of guessing the plain text from signal key and the ciphertext equals to the decomposition of the product of 2 large prime keys. This key setup is done once when a user establishes their public key. The exponent E is usually fairly small. Just must be relatively prime number of moduli of n. Need to compute its inverse to find D. It is critically important that the private key Kr is a PDQ. Is a set of PDQ is kept secret, since if any part becomes known, the system can be broken. Note that different users will have different moduli of n. Okay, let's go with the AES cipher by Ringdale. This is one of the predefined and the most popular cipher encryption standard, advanced encryption standard, also known as advanced encryption standard. And the Ringdale proposed this AES define a cipher in which the block length and the key length can be independently specified to be 128 or 192 or 256 bits. These AES specifications uses the same 3 key size alternatives but limits the block length to 128 bits, and it is an iterative cipher, operates on entire data block in every round rather than Feastel. Feastel is which operates on halves at a time, like bits and halves. It won't take the complete cipher at a time, and was defined to have characteristics of resistance against all known attacks, speed and code compactness on a wide range of platforms, and design simplicity. This is a overall AES process which is being defined earlier, and in this process we have the data Like if you take the 256 bits or 128 bit or 192 bit of data, and then the data is being divided into a secret key. Some part of the data is divided into secret key and some is divided into plain text, and then the data on the key has been ciphered and it is converted to a ciphertext, and this ciphertext will be of 128 bit or 192 bit or 256 according to the data input which is given by the user. When you come with the AES structure, the input of the AES encryption or decryption algorithm is a 128 bit block as a square matrix of bytes. This block is copied into a state array, which is modified at each state of encryption or decryption. After the final state is copied to an output. What is state? The state, it is an operation performed in a two-dimensional array of bytes. The key is expanded into 45, 52 or 60 lots of 32-bit words with 4 used in each round. Note that the considering of bytes with a matrix is by column. So let's take an example. The first 4 bytes of 128-bit plain text into the encryption cipher occupy the first column of the in matrix. The second 4 bits occupy the second column, and so on. Similarly, the first 4 bytes of the expanded key, which form a word, occupy the first column of the W matrix. And the initial XOR operation and the fast XOR operation are being implemented with the lookup operations. The key and the data are being scrambled and being done with the XOR operation. When you go with the encryption process, the data and the key are the ciphertext or the cipher key is being stored in the state. The state then adds a round key. The data computation then consists of an add round key step, then 9 or 11 or 13 rounds with 4 steps, and a final 10th, 12th or 14th step of byte byte, like the sub bytes, shift rows and the mix columns and the add round key are being performed accordingly to encrypt the cipher key some more reliable. This can be viewed as alternative XOR key and sample data bytes operation. All the steps are easily reversed at the last and can be effectively implemented using the XORs and table lookups. And whereas in the final step or the 10th round, the add round key or the mix columns is being eliminated, and the no mix columns operation will be performed at the time of the final round. Okay, now let's go with the 4 steps which are being included in the encryption and the decryption process, the AES advanced standard encryption process. And let's go with the substitute bytes. What are substitute bytes? We now turn to a discussion of each of the 4 transformations used in AES. So in each stage we mention the forward encryption algorithm to inverse decryption algorithm and the rationale for the design of that stage. The substitute byte stages use an X box to perform a byte to byte substitution of the blocks. There is a single 8-bit wide S box used on every byte. This S box is a permutation of all 256 8-bit values, constructed using a transformation which treats the values as polynomials in GF of 2 power 8. However, it is fixed, so really only need to know the table when implementing. Decryption requires the inverse of the table. The table was designed to the resistance to no cryptanalytic attacks. Specifically, Ringdale developers sought a design that has a low correlation between the input bits and the output bits, with the property that the output cannot be described as simple mathematical functions and out input and no fixed point and no opposite fixed points. You can see up here the S box and the block or the data from the first block has been converted with the block in the second data, and these matchings are being done with the respective X and the Y columns, which are the fixed values in the X box. The byte substitution operation on each byte of the state is independent, with the input byte used to index in row or column in the table to retrieve the substituted value. Oh, let's take an example and substitute byte the transformation from text to text. You can see the EA has been converted to 87 and 04 is converted to 42 and 64 to 44D and 85 is to 97 and so on. These values are being encrypted hidden in the table, and this is being watched accordingly from the table from the given data initially with the X and Y axes which are available in the S box. Now let's go with the shift rows. The shift row trays provide a simple permutation of the data, whereas the other steps involve substitutions. Further, since the state is treated as a block of columns, it is this step which provides the diffusion of values between the columns. It performs a circular rotation of each row of 0, 1, 2 and 4 places for respective rows. When decrypting, it performs the circular shifts in the opposite direction to each row. This row shift moves an individual byte from one column to another, which is a linear distance for a multiple of 4 bytes, and ensures that the 4 bytes of one column are spread out to 4 different columns. Whereas in the shift rows, when you go with an example, this is the brief sketch of the shift rows, and you can see up here the first very bit. This is also known as the root shift. The root shift is a kind of shifting position, is that the very first bit is being moved to the last, and the last is moved forward, and the third and the second is moved forward, and so on. This process repeats in 3 different types in 3 different rows, and each row will be shifted with the previous column or the previous row which is available in the given data cipher. An example of the shift rows this is an example from the shift row from the text. When you come with the mixed columns, each column is being processed separately. The forward mixed column transformation, called the mixed columns operation in each column individually. Each byte of a column is mapped into a new value that is a function of all 4 bytes in the column. It is a substitution that makes use of the arithmetic over GF of 2 power 8. Each byte of column is mapped into a new value that is a function of all 4 bytes in that column. It is designed as a matrix multiplication where each byte is treated as a polynomial of GF of 2 power 8. The inverse used for decryption involves the different set of constants. The constants used are based on a linear code with maximum distance between the code words, that gives good mixing of the bytes with each column. The first number with the first number in the second column, the second element with the second element in the second row in the second column, and so on. Combined with the shift cross two step provides good avalanche, so that within a few rounds all output bits depend on all input. In practice, you implement mixed columns by expressing the transformation on each column as four equations. Uh, to compute the new bytes for the column, yeah, for that particular column. This computation only involves shifts, XOR operations, and conditional XOR operations. The decryption computation requires the use of inverse of the matrix, which has larger coefficients and is thus potentially a little harder and slower to implement. The designers and the AES standard provide an alternate characterization of mixed columns, which treats each column of state to be a four-term polynomial with coefficients of GF of 2 power n. Each column is multiplied with a fixed polynomial of AX given here. It's labeled as CX in here. It's a constant though. Wish list. This is useful for analysis of the stage that matrix decryption is also thus requires for implementation. The coefficients of the matrix are based on linear code with maximal distance between code words, which ensures a good mixing among the bytes of each column. The mixed column transformation combined with the first row transformation ensures that after a few rounds, all output bits depend on all input bits. In addition, the choice of coefficients in mixed columns, which are all 01, 02, or 03, was influenced by implementing considerations. Okay, now let's go with the round key. Lastly is the round key stage, which is a simple bitwise XOR of the current block with the position of the expanded key. Note this is only just a step which makes use of the key and obscures the result, hence must be used at start and the end of each round, since otherwise could undo the effect of other steps. But the other step provide confusion or diffusion nonlinearity. That you can look at the cipher in a series of XOR and the key that scrambles permute a block repeated. This is efficient and highly secure, it is believed. And the other thing is the round key. When you see in the process, the round key isn't performed. The add round key is performed in the last bit, but then the mixed columns, the performance of the mixed columns is being absent in the final round in the encryption process. Whereas in the AES round, you can see this is a brief description of the AES round and the strays, subbytes, and the shift rows and the mixed columns and how the performance. This sketch gives you the data and the encrypted key according to the stage and step-by-step process. Now view all the internal details of AES round, showing how each byte of the state is manipulated. Whereas in the AES key expansion, the AES key expansion algorithm takes an input 4-word key and produces a linear array of words, providing a 4-word round key for the initial add round key, and each of the 10, 12, or 14 rounds of the cipher. It involves occupying the key into the first group of 4 rounds and then constructing subsequent groups of 4 based on the values of the previous and the fourth backwards. The first word in each group of 4 gets special treatment with rotate plus x s box plus XOR constant on the previous word before XORing the one for the 4 back. In the 256-bit or bit key or the 14-round version, there is also an extra step on the middle word. And the AES expansion. Here we go. The AES expansion, as explained before, the first row goes with a round with the final segment, and then the shift will be processed. The first block of the AES key expansion is shown here. It shows each group of 4 bytes in the key being assigned to the first 4 bits. Then the calculation of the next 4 words based on the values of the previous 4 words, which is repeated enough times to create all the necessary sub-key information. Okay, let's go with the AES structure, and this is the brief sketch of what we have learned up till now, the advanced encryption structure. The structure in here, the add round key and the shift rows and the mix columns are being processed, and the expand key is being implemented and with the plain text which is being implemented as a ciphertext. This is the encryption process, and this will be the decryption process. The cipher consists of n rounds, where the number of rounds depend on the key length. 10 rounds for 16-bit key, and 12 rounds for the 24-byte key, and 14 rounds for 32-byte key. The first n-1 rounds consists of 4 distinct transformation functions: sub-bytes, shift rows, and mix columns, and the add round key, which are described subsequently. The final round contains only 3 transformations, and there is an initial signal transformation, or the add round key. Before the first round, which can be considered round 0, each transformation takes one or more 4x4 matrix as input and produces 4x4 matrix as output. And this figure shows that the output of each round is 4x4 matrix, and the output of the final round being the ciphertext. Also, the key expansion function generates n+1 round keys, each of which it is a distinct 4x4 matrix. Each round key serves as one of the inputs of the add round transformation in each round. As we go into the decryption process, the AES decryption cipher is not identical for the encryption cipher. The sequence of transformations for decryption differs from the encryption, although the form of key schedules for encryption and decryption are the same. This has the disadvantage of 2 separate software or firmware modules are needed for applications that require both encryption and decryption. Therefore, however, an equivalent version of the decryption algorithm that has the same structure and the encryption algorithm within the same sequence of transformations as the encryption algorithm, with transformations replaced for their inversion. By constructing an equivalent inverse cipher with steps in same order as for encryption, we can derive a more efficient implementation. Clearly swapped, the byte substitution and the first row has no effect, since work just on the bytes. Swapping the mix columns and the add round key steps require the inverse mix. and this makes the decryption key schedule a little more complex with this construction, but allows the use of same H or W or S or W for the data encryption or decryption computation. Okay, what we have done in here, we have the summary of various encryption algorithms and AES selection process, key and unit to keep the key safe. The details of Ringdale, the AES cipher, has been learned. You can look into the deeper information about the AES encryption or the AES cipher in Ringdale.com, and go into the link of Ringdale and you can get a brief description about it. Look at the steps in each round and the key expansion. The key expansion is an additional input for this AES structure, so it has to be done very efficient.